Swayam Prabha. Digital India. Educated India.
Okay, good morning, everybody, and thank you for being here. Thank you to Sagar, who has been taking care of bringing me here for this presentation. And what we're going to talk is about catalysis in general for several things. So, I mean, the title is clear. You see that we're talking about characterization of heterogeneous catalyst, talking about the bulk, surface, and then in situ and operando methods. This is a 2 weeks course, so at the beginning I will begin more about what catalysis is, basically following up on what Sagar has already been telling you, and giving also the perspective or where we are and how and why catalysis and chemical engineering is important. But before I do that, I also like to tell you where I come from. So basically, I am coming from the Spanish Research Council. Okay, so I belong to the CSIC, which is the Spanish National Research Council. And basically, we are based essentially in Spain. So these are like the headquarters over there. And we have 125 institutes all over the world. Actually, we even have an institute in the South Pole in the Antarctic, which is open only in summertime. And about the figures about the CSIC, basically we are the 7th in the world ranking of international research organism and top 5 within European Union projects. And we're a big community, like 13,000 people distributed in these 125 institutes, all of them in Spain except one in Italy and one in the South Pole. And because we are 125 institutes and we are dealing with all the fields of knowledge, we are also creating and developing virtual institutes, or what we call technology platforms, which basically are connecting people from different areas of knowledge in topics that are cutting across. So basically, okay, this is my institute, not so special, and we are based downtown Madrid. Now, there's different fields of knowledge where we are promoting cross-discipline knowledge, is some of them within energy and industry, some of them about health and environment, some of them about digitalization and future society, and others about Earth and ocean systems. Within the CSIC, we have people working in human sciences, biology, physics, astronomy, chemistry, materials, mathematics, everything. So among these big fields of knowledge, some of relevant platforms from the point of view of catalysis is, for instance, within energy and industry, we have a platform about sustainability, a sustainable platform, where we are bringing people from natural resources to catalysis and engineering. And we will briefly comment about why this is important. But I mean, you are chemists, you are chemical engineers, so I'm sure you already figured out why. When it comes to health and environment, we have this global health platform, which is bringing, again, interaction. We are now working with virologists and with people at molecular biology, which we didn't think of maybe before COVID time, but now we're actively involved in indoor air quality, but not only chemical, but microbiological indoor air quality. Digitalization is going to be a revolution everywhere, because now we are dealing with the data that we are obtaining, but in the future all this data must be available, must be usable, and that means that the way we store our data and all the information associated with this data, the metadata, really have to reflect the experiment, the person, the conditions, everything, so that all these things can be machine readable and enable further analysis. So that is also like another interesting approach, bringing again people from all disciplines. And then about Earth and ocean, there is also a lot of oceanographic research with the ships we have and with complementary collaborations. Okay, so that's enough to get a global view about the CSIC. And now we are going to talk mainly about the kind of research that I do, and that is the topic of this course. And you will see during these days that mainly the emphasis of my research is about in situ and operando methodologies. But before going into that, it will take a while, because before we have to talk a little bit about the frame, about chemistry, about characterization techniques, about the catalysts themselves, and different complementary aspects. And before that, of course, we have to settle some bases. You know that the chemistry is the science that studies the matter and its properties. And what we do in catalysis is to change molecules. So in the end, we are dealing with the art of changing, of converting the matter. And finally, chemical engineering ultimately is applying all these developments of catalysis. Sagar has already told us how important catalysis and chemical engineering is globally. And I want also to elaborate on that. And I want to elaborate on that also from a very long perspective. He was telling us already that catalysis has been there even before we knew there was catalysis. But also, if you look at the population, you will see that the population has been increasing continuously on this planet during the last millennia. And now the most interesting thing is that the number of people living on Earth has increased dramatically, particularly in the last century. This is a double logarithmic plot, so the number of people through the time is rocketing. Also, not only that, here you have that right now there is more people living than may have been living in the previous centuries, which is amazing. And it is not only that we are more, but the average age, it used to be something like 25 years old. I should have been long death and you are about to die. But currently, things are not like this. The average age is something like 80 plus or 70 or 60. So we are more and more people and we live longer. And do you know why? Because of science. And if I ask you in particular why we are so many people, and I ask you something more specific in the answer than science, what will you say? Why can so many people live now? And this is something that has happened basically in the last 100 years. Sorry. Medical science will really help you to keep people living longer, but you have to keep all these people alive. I mean, if there is no food for everybody, I mean, you can have the best medicine, but if there is no food, they will die. So the most important thing is actually a molecule called ammonia. And why is ammonia important? What can we use ammonia for? Fertilizers, exactly. And that is a process that basically was developed like 100 years ago, the Haber-Bosch process. And the most important thing about this Haber-Bosch process is that from ammonia you could make fertilizers, ammonium nitrate. And I could put like a million of tons, whatever. It's good enough to know that we increased from 1.6 billion people to 6 billion people in 100 years. That is okay. Many tons of fertilizer is okay. But I have a much more informative detail because all these fertilizers, because of the ammonia, is helping the plants to fix what element? Nitrogen. Now, in your body, how much of the nitrogen that you have is coming from a factory? What percentage? Say. I mean, a value between 0 and 100, if that helps you. Make a guess. What percentage of the nitrogen in your body comes from a factory? Sorry? Well, not. But the plants fix the nitrogen through the fertilizers, and actually, the amount of nitrogen that we have in our body coming from factories is 50%. So half of our body is essentially an industrial product. So that is how important the chemical industry has been, is, and will certainly be, because this is a game changer. All of a sudden, you could feed huge amount of people. Famine was no longer an issue because people could eat. And with medicine and with all catalytic developments, for water purification, air purification, you increase everything. But you know that this is not only a demographic explosion. The ammonium nitrate is also an explosive, a powerful explosive. You remember, like a few years ago, there was an explosion in the right photo in the harbor of Beirut because they had a big store of ammonium nitrate, and there was an explosion. That basically this yellow line is telling you where the harbor line was and where the building was. So the explosion is huge, but it's not the first one, and perhaps not the last one. But for instance, the first one of this kind was in the BAS factory in Opau in 1921, 100 plus years. It was the first ammonia factory, and there was an explosion. So this big hole there is where the explosion happened that killed 600 people in the factory. Other big explosion of ammonium nitrate happened in Texas Harbor in the 40s, again, killing 400 plus 500 people. So the fertilizers are a source for demographic explosion, but also all kind of explosion. But this is also a message for science. What we do can have multiple uses. And one important thing from the point of view of science is to help and to contribute to the best use of everything. And also to take not a responsibility, but also the perspective. Back in the 70s, there was a concern, and the Club of Rome, which was kind of a think tank group of people from expert people from different fields of knowledge, they met and they made an analysis and said, okay, we are an increasing number of people with an increasing demand of material and energy resources, and we cannot do that forever. There will be a moment that the energetic and the material supplies on Earth will not be enough for us. So there will be a limit to growth somehow. And that was published back in the 70s, and they were talking about energetic and material resources. So somehow it was one of the key messages where people start to become aware about sustainability, about to make sure that things can be made. They made an updated edition like a few years ago, but I mean the main figures, basically we're talking about an inflection point about 2006, where basically depending on what we do, we may eventually collapse, we will keep on growing, or we will level off. And what determines that? Well, it determines that mainly science, how the scientific technology allow us to cope with that. But of course, you know that sometimes science knowledge grows faster than the society knowledge, and how the society assimilates our knowledge. But we are the enabling tools, and then we, of course, need the cooperation of the society to implement these things. And that means also that we have to share our knowledge and our understanding on how to do these kind of things. Because we may think that we are sailing on a never-ending ocean where everything is unlimited, but in the end, we are in a small planet, and actually, this planet is isolated. You don't have many things outside. Well, there is a lot outside, but empty, and you cannot live outside of here. So whatever you do, you have to do it here, and you have to optimize the resources that you have here. And that's why it's very important basically to share this kind of application, and how we have been responsible for having so many people, but we also have to make sure that all these people will eventually not collapse because of us, our children, grandchildren. And the key tool, the key science that will essentially help us to do these kind of things is catalysis. And Sagar was already telling you some figures. We're talking, these are already all data, but that's good enough. We're talking about $8 billion from the world GDP. And from that, 12 out of 80 corresponds to catalysis. That is a very big share of the world economy. Such a big share that it compares to the great economic blocks in the world. So the economic dimension of catalysis is like the rest of Asia, China, Western Europe, or the USA. That is very important. That is telling you something. Not only that there's a lot of money behind, but that means that it does really have an impact on us, on our society, on our life. What is the catalysis industry doing? Well, many things. This is a bit outdated. That was a forecast from 97 to 2000 plus. But basically, catalysis is working on several complementary things. Chemical production of commodities, and then refinery, because in the end, most of the chemicals are coming from petroleum, from crude, and that means a refining process. Basically, the catalysis research share is distributed between many things, essentially chemicals, and the chemicals are like a key products along with the refinery, and we are dealing on the one side about making polymers, and on the other side about remediation of things, about compensating for excess pollution, remediating pollution. So the perspective is quite similar, and it's probably not going to change that much. And I also want to make one more reflection on demographic explosion. 10,000 years ago, they thought that there were like 10 million people in total. Nowadays, 10 million is basically the number of scientists that we are on Earth, and a few more coming now from you. So that is also something interesting, that right now there are as many scientists on Earth like people was living around 10,000 years ago, which also gives you some kind of perspective of things. There are many chronologies about the catalysis with the key developments, but I mean, there's no need to go through that because Sagar was showing much better slides telling the evolution of that. And also the recognition to the society. If you look at the Nobel Prize winner awards in the past few years, you have seen a number of them. Many of these names are familiar: Arrhenius, Sabatier, Haber, Fischer, Langmuir, Hinshelwood, Ziegler, Natta. I mean, all these names are important. And also the kind of research they are doing, it was not in one only sense. Some of them was more biological, another one was more about surface science, another one was more about polymer synthesis. So that is also giving you a flavor, anecdotic, because Nobel Prize in any case is a little bit anecdotic of people who has got a major highlight. But this is also telling you many important things about how catalysis is evolving. And in the end, catalysis is at all crossroads. It is at the junction, at the fork of everything. It takes a little bit of analytical chemistry. It uses physical chemistry to characterize. It uses inorganic chemistry materials to run reactions. It typically runs organic chemistry reactions. But all these things have to be scaled up, which means that it also needs chemical engineering to enable those things. And ultimately, this is connecting with the environment on one side because we optimize our processes to minimize the emissions, and on the other side because we work on remediating these emissions and these kind of contaminations. So we are at the fork of all the roads, and this is something which is amazing and also opens opportunities that we can do research on almost any topic. And that is something which I think it is important. Now, whatever we do in catalysis, there is a vision, which is basically we want to know what we are doing. It's not like, what is, I don't know, I did this, and I got that. Why? Who knows? No. You have to know, you have to go beyond that. You need the understanding, because once you do that, you want to reproduce it, and you want to use this knowledge to go beyond and make other applications. So you want to design more catalysts, and in the end, you have to know what is happening, and that means characterizing the catalyst. And to characterize the catalyst in the real working conditions, because you heard the definitions, and all the pioneer definition of catalysis is basically giving an ideal concept of catalysis. What was the common word that all the definitions that Sagar has told you appeared in every single case? What is a catalyst? That's a question. But there is no answer. What is a catalyst? Say something. Nobody? For instance. And what happens with the catalyst? Without changing itself. But is it true? No, exactly. So all the definition of a catalyst, without changing itself, it's not affected, it's not transformed, it doesn't die. Ideally, it is like that. At the beginning, there was the activation. Yeah, okay, there's some coke on it, but the catalyst is a nice guy. It never changes. It changes, it ages, it deactivates. There is falling, there is transformations. Not only that, it is that the catalyst itself, it looks different during reaction. So if you characterize a catalyst just the way it looks like on your table, or the way it looks like in your reactor at 300 degrees with propane, oxygen, it looks different. It changes, and it ages. And so this is the reality. So the very definition of catalysis is actually an ideal definition. Some people say it's wrong. I mean, I wouldn't say it's wrong, but it's just the ideal concept. For the time life of the molecules that live milliseconds, the catalyst is indeed stable, but for us, the catalyst is aging, is deactivating, and it's transforming. Okay, the audio is okay? Good, okay, I got a message here, thank you. And that means that we have to characterize things and to model things. And also, we have some people from theoretical chemistry. I always like to talk about computational chemistry from the point of view that they give us the psychology, the rationale of what is happening behind the catalyst. somehow like a psychoanalysis of the catalyst, because it brings you the rationale of why a catalyst is behaving like that, why I'm getting this kind of spectra, why this additive is having this effect, why this reactant. So it gives you the rationale. Somehow it's kind of the psychology of what is happening and why it is happening. And also, we want to do things as efficiently as possible. That means that we want to optimize the use of our resources, not only to become active on something, but efficient, to minimize the use of energy and the use of materials to do something, which basically is the concept behind process intensification, which actually is not more intense for you, but is less intense for you to get something. And priorities for catalysis, well, it's everything. You have seen that catalysis is touching every single thing. Traditionally, it was used for fossil fuels to convert things, okay. But also for the light fraction, like a natural gas, also to make all kinds of commodities. Lately, renewable things, biomass, so we have to deconstruct biomass, then we have to recycle, we have to use it. So it's a completely new chemistry. Petrochemistry without petroleum is being developed. And that means all kinds of processes from biomass, pyrolysis to bio-oils, aqueous phase reforming, whatever. And also increasing energy efficiency by the use of electromagnetic radiations, photocatalysis, or also all kinds of radiations like microwaves or whatever, or also electrocatalysis. Some of you are working on these kind of things as well. And it also has implication on the health and on the environment. So what are the priorities? Well, everything is a priority for catalysis. There was a time like a key topic was, okay, low emissions. This kind of catalyst like Toyota filter with the platinum barium to reduce the NOx. Some people say, no, but this is phase out. No, I wouldn't say it's forgotten. There is a transition. We are decreasing the use of combustion engines, but that doesn't mean that combustion engines will disappear tomorrow, and not even after tomorrow. So this is the technology for efficient cars and automobiles still remains as a need. We have to follow up on that side. The same thing happens with air quality, indoor air quality, outdoor air quality. Mainly when the climate is becoming increasingly extreme, like for instance here in Madras, you want to have a good temperature inside, but you want to do it in an energy efficient way. So the best way to keep a good comfort, hydrothermal comfort inside here is that you close and you have a very good system controlling temperature and humidity. But people typically has the habit of breathing, and when you breathe, pathogens come out and you share your pathogens with all your colleagues. So then you need to renew the air. But if you renew the air quality will be better, but then the building is less efficient because you are continuously getting fresh air from outside. So you need also systems to purify the indoor air without need of renewing the air. So in the end, everything is connecting health, energy, environment. So there are many fields where you will certainly have needs of application. So this is even more important than what you thought. And of course, now with electrification, hydrogen as a vector, fuel cells, or just hydrogen, just to use it as an energy vector is very important. So there are a lot of applications where catalysis is. Now, we're always talking about nanocatalysis because nano is basically a dimension where the property of the matter changes. You have a confinement, you have a surface to volume ratio, and the properties will change. And that's good. We use it, we need it, that's very efficient to us. But, and for the community for a number of years, nano things was cool, was fashionable, was nice, until they start to get worried. Oh, but these nanos are everywhere, I'm breathing in and having problems, whatever. So there's some people which is moving from this nanotechnology to no technology. Now, we have to avoid that. We have to be sure that people is not afraid of technology, because now the problem of science is that people is getting into any topic and disconnecting. So we have to make sure that the work is good and to avoid this kind of no technology and to assure that things are good. One general view about changes in general, about today is more generalist. We're talking about many things, and then tomorrow we will go more into catalysis and characterization. Well, CEPSA is a Spanish petrochemical. They just changed the name to Mueve in early this year, but the name is CEPSA. And they have a pretty nice view about how things are changing in the new frame of renewables. We talk about refinery with fossil fuels. We're talking about biorefineries. But all the way from refinery to biorefinery cannot be made in one step. I mean, nature may not be linear, but at least it is continuous. And the same thing happens with industry. You cannot say, okay, I forget all the fossils and I jump into something new, and the technology for it, well, I will develop. No, you cannot do that because you end up emitting much more CO2 than the one that you want to remediate. So you have to make things much more efficiently. So the refining process is like this. You can get all kinds of products, and basically what you are getting from there is very well known. Basically, depending on the distillate, you get lighter things like gases or gasoline, kerosene diesel, which is heavier, or fuel oil, all the way down to asphalts. And also a big collection of chemicals in general. Which kind of chemicals? Well, you know, out of through hydrodesulfurization, through benzene, and then you can make like cyclohexane, and you can make nylon, or you can make PET, which is of course everywhere around us, in our clothing here, everywhere. And LAPSA, which is linear alkyl benzene, and many other products. And you know all these things. LAPSA, for instance, you use it for washing clothing, and this is something that somehow connects Spain and India, because major producers of linear alkyl benzene are basically in Spain CEPSA, and over here Tamil Nadu. So you have like two companies which are among the key producers of linear alkyl benzene, which is used for surfactants in detergents. And for the PET, is one of the most important plastics, which is being used for bottles and for everything. So there are a lot of chemicals which are being produced that we are going to use, that we are obtaining from petroleum, and that we need them. We cannot get rid of those. And so there is another question. What do you think in the frame of sustainable? Should we make plastics that are biodegradable, or should we make plastics that can be recycled and reused? What will be a better choice? Sorry? Both, indeed, both are good. And which one is more attractive conceptually? Sorry? Recycle, yeah. Yeah, because when you make something which is biodegradable, okay, you toss it around and it will disappear within days, weeks, whatever. Okay, but that's a major investment, an expensive thing that you make just to be degraded in the soil. If you make something that can be used again, you are much more also efficient in the use of your energy resources and in the use of material resources, because this is not going to be misplaced, whatever. Something that you are going to use, and that is also something important. So you have to do two things, but the perspective of recycling, upcycling, and whatever from a residue is important, because this is the main source of materials that we have ourselves, our residues, our garbage. So that is something important. And for that reason, there is also another idea, which is the co-processing, where you are using fuel and you are adding to the fossil fuel sources for the refining all kinds of recycled materials that you are obtaining from plastics, from cooking oil, from whatever. And that is an important way also of making a progressive change in these kind of things, so that the classical refining will no longer be just taking fuel from fossils, but they will get like a little bit more from plastics, from city residues, from biosoils, biomass residues. All these things have to be integrated. Can you do it directly? Can you go to the classical refinery and dump those things in the factory? No. You have to change the technology, you have to change the catalyst, because the catalysts are used to process a kind of crude, and it's not the same crude from Iran than a crude from Mexico, than a crude from wherever. They have different compositions. And in this case, when you are dealing with circular feedstocks, with these materials that you are recycling, well, things will also be different on whether you are using, for instance, oils that you can get from cooking oil, or get oils from the pyrolysis of plastics, or even tires from the automobiles, or from biomass in general, or all kinds of city waste. So all these things will have different sources, and ultimately even producing hydrocarbons and oxygenates out of CO2 and other environmental molecules. So you have to do some kind of treatment to have this in a much more usable way, to get it into the refining process, to get finally the kind of chemicals you need out of a residue, not only out of the fossil fuel. And when you are doing that, things, I mean, everything is not plain sailing, as they say, so you have problems. And basically, some of the problems you have is that for fossil fuels, you very well know which kind of contaminants, which kind of metals, which kind of things you have that will affect your process, will poison your catalyst, and so on. But when you have so many sources, because basically you are working from the garbage, you can get all kinds of things. And that can be a problem. You can have different kind of problems with a much higher oxygen content in this kind of biomass compared to the fossil fuel. And you may also have more problems of corrosion because of the chlorine that can be there, or different kind of elements. It depends on where you're working with, so that is not trivial. So when you are doing this process, you have to refine it, but depends how you refine based on the source of the material that you are dealing with. So one of the ways to do for many of them is pyrolysis, where you basically, in the end, you end up getting an oil that will be processed closer to these industrial applications. But which kind of bio-oils you can obtain? It depends a lot on which kind of source, whether you're dealing with wood, with straw, with algae, with agricultural residues. Some of them have a higher lignin, others have a higher cellulose lignin. Some of them are more fluid, other ones are much more viscose. So you have a great variety of things, and you have to cope with all these things. So it's not so trivial when people say, oh, okay, let's forget about fossil, let's go into renewable. You cannot do it in 1 week, even in 1 month. You probably need a bit longer. You have to do it, but you cannot rush. You have to do it with knowledge. Because the biomass pyrolysis oil, this py-oil word, is basically something that has a lot of contaminants. Here you have a few of them, depending also on the source. But the water is a key component. Organic acids are a component. Aldehydes and ketones, phenols, and other kind of hydrocarbons. That can be a headache. And when you are recycling plastics, it's the same thing. How many plastics you know? Well, probably all of these you are used to it. You have seen polyethylene, polypropylene, PVC, polyestyrene, and others. All of them can be recycled to a higher or to a lower extent. Some of them are easier to recycle, others are more difficult to recycle. That depends on many things, but the first of all is on the chemical reactivity. If you are dealing with polyethylene or polypropylene, you only have carbon-carbon bonds. Those are much more difficult to break. But this is a much more clean molecule because composition is much more simple. In other cases, like nylon or like esters, or you have ester bonds, or you have amide groups, whatever, chemically they are more reactive. So you can break them, you can attack them. So you have more easy chemical processes. But sometimes it's a mechanical processing, sometimes it's a chemical processing. So things are changing a lot. But the key message is that the plastic is a misplaced resource, something which is tossed away, but this is huge amount of raw material, but not very homogeneous. And that is the big challenge for future catalysis. And that's the problem when you look at the pyrolysis oil from plastics. It's not the same pyrolysis oil that you're getting from a given plastic or from another plastic, because you can have all kinds of contaminants. Here you have a summary of them. Don't worry, all of them are like a headache for a catalysis person, because you will have poisoning problems. And you can even make it more difficult, because then you have plastics from electronics, from this, from that, whatever, and then this is a nightmare because you are adding heavier elements, additional components. And then you can see on this table, we are talking about the presence of iron, of nickel, of phosphorus, antimony, silicon. I mean, these things make that recovery of plastics is a great challenge, but it's not trivial. So we really have to work with that. And of course, if you are dealing with a pyrolysis that is coming from plastics, you will have a deactivation for one reason. If you are doing it from biomass, you will have another problem of deactivation problems or different kind of challenges on the deactivation. So in the end, you can get all these pyrolysis oils in a refinery, yes. And here you have like these little red and orange dots where basically you can use everything or selected cuts, different parts of the distillates in different kind of processes. So, but the key point is, okay, I'm doing that. I'm using renewables. But am I closing the balance? I mean, at the end of the day, the total amount of CO2 that I'm emitting is higher or is it lower? Well, that is also important. Because there is a certification for that, which is this ISCC, which is International Sustainability and Carbon Certification, which is basically making an assessment of that, how efficiently you are actually reducing the emission of CO2, taking in mind the complete life cycle of the process. which means, that can be applied to all kinds of industries. And for instance, if you have from vegetable oil, you have this kind of process. And vacuum gas oil, this is like a very light distillate from fossil fuel. You have a given process where basically you have an efficiency of 0.9. Okay. What happens if you are adding a biomass there? For instance, like 100 kilograms for every ton. What is the balance? Am I still decreasing the emission of CO2, or am I increasing the CO2? And there are many things to have in mind. And this is also like one of the big challenges, to be sure that what you are doing is energy efficient. Because I'm just using biomass, I'm using the CO2. The concept is good, but the reality, the devil, is in the details. And actually, here you have, I'm sorry, this is actually in Spanish, but this is a simple numbers. For 1 barrel, which is 160 liters, the amount of energy that you need to make 1 barrel of diesel, fossil diesel, is basically the equivalent of 130 to 170 kilograms of CO2 to make a barrel of diesel. Now, to make a barrel of biodiesel, if you don't consider anything, the emissions are much higher. It's 250 to 400 kilograms. Why? Because in the diesel, fossil diesel, you are using a crude that were trees millions of years ago, and that the nature have been processing for you during millions of years. So you take it and you make the process. In the case of the biodiesel, you have to harvest, you have to water, you have to do many things before this goes to the factory. A lot of things that you don't do from the fossil. Now, that is an investment in energy, in time, in water. So those things are important. And before you make the complete, okay, how much carbon I have captured, the emissions is almost twice in the biodiesel and diesel. So this is very important to be sure that the whole process is efficient. And in the best case scenario, you are pretty much breaking even or decreasing a little bit the emission of CO2 with biodiesel, but you have to be very efficient. But there's another factor, that the watermark. You are dealing 1,000 to 2,000 liters of water per barrel of diesel, but 10,000 to 20,000 liters of water, 10 times more per barrel of biodiesel. So the water investment, the water footprint, is 10 times higher. Now, in this case, there's no way you're going to break even. So you have to keep in mind all these things, and probably think that biodiesel can be an interesting thing, and you really have to think of sustainability because you have to do that, but do not rush in where the angels are afraid to step. Make sure that you break the balance, that you close the balance, and that things make sense, because that can be also a challenge. And we have to do it. I don't mean we don't have to do it, but we cannot rush. We have to make sure that the process is right, and we don't want to break all the factories or end up emitting a lot more than what we want to compensate. And that is something very important. And that's why this progress in the refining to this co-processing until we go into alternative things is very important. Energy source will have to change. The source of chemicals, we will still need all these kind of raw materials. But if we come to a general view of things, we can make a couple of easy questions. Is oxygen good? Yeah, don't be shy. Yes, it is. I mean, we need it. We need it. Of course, it's good. Is water good? Yes, it is good. Is CO2 good? Yes, actually, it is good. I mean, too much of CO2 is not good, but we need the CO2 for the plants to grow. So, in the end, everything is like, we are scientists. From the point of view of the society, maybe people say, okay, CO2 is bad as an absolute definition. But it's like everything. There's nothing is too good or too bad, depends on the dose. And a right amount of CO2, you need it. A bigger amount, no. And we are at the point that probably this will have a significant impact on the climate. So that is something to bear in mind. CO2 is good in the right amount. It's like drinking. Okay, you can drink a cup of wine, but not 2 liters because. So you need the right amount, and that is important. And also how we are doing that, because if you compare different things, like say, okay, shipping cargo is okay, it's quite energy efficient, but if you go on a cruise ship, the emissions per kilometer, we're talking about one of the highest emission per passenger is in a cruise ship. If you are taking a flight to go, I don't know, from here to Bengaluru, the emissions is very high. But if you take a flight, not to go from here to Bangalore, but to fly from here all the way to New York, a long haul flight, then the emissions per kilogram is lower. So, no, I don't fly. Well, depends. I mean, if you're going to go to New York by car or by ship, you will be emitting a lot more CO2 than if you take a flight to New York. So, again, it's the same thing. You're not going to fly to go just like 2 hours from here, but you're going to fly to go far away. And the same thing is, like for instance, with the internal combustion engines, like diesel car or gasoline car, they emit about 170 per kilometer. Okay. What happens with the electric car? They emit 47. So this is like 3-4 times lower amount of emissions in an electric car than in a combustion car. Or plug-in cars or hybrid cars, they're talking about 70, which is about 1/3 of a combustion car. So even not only pure electric, but hybrid solutions are giving you also quite a convenient deal compared with the combustion cars. So do you have to go all the way to electric cars that do not emit? Maybe, but these cars get the energy from somewhere. So I'm not emitting CO2, but every time I plug it, I may or I may not, because we don't know where that electricity comes from. And we will see another consideration also about electric cars. Because usually, when you think of combustion cars, you think something like that with things coming out. And when you think of an electric car, you think of something fashionable like this, which is not emitting. But in the end, actually, nowadays, they don't look that different. And even from the point of view of emissions, you don't know. I mean, it looks like that, but what are exactly the emissions now? A car like this, the gas mileage can be like 5 liters per 100 kilometer. Okay, that's very good. It's not like before it was 7, 8, or 9 liters per 100 kilometer. The mileage is good. Now, in this case, the mileage is infinite because this is electric, so there is no fuel. It basically runs on electricity. But we also have to bear in mind something. For instance, what are the emissions of a car with a mileage of 6 liters every 100 kilometers? You have this car during 100,000 kilometers. Okay, it will be emitting something like 16 to 14 tons of CO2, depending on whether this is diesel or gasoline. If the mileage is better, it will be even lower. But okay, keep this value, about 15 tons of CO2, 100,000 kilometers in your car, gasoline or diesel. How much energy does it cost to fabricate an internal combustion engine car? About 6 to 10 tons of CO2, essentially. So you buy your car, you are emitting 10 tons of CO2. You buy an electric car, and the electric car will not emit CO2 running, but fabricating it is more energy intensive. So you are emitting 10 to 15 tons of CO2. So let's everybody sell our combustion cars, and tomorrow everybody will buy electric cars. All of a sudden, everybody is emitting in 1 week the same amount of CO2 that you will emit with your combustion car during 100,000 kilometers, which may be 10 years, 15 years. So you have to keep these things in mind. That something that we cannot keep for the future, the internal combustion engine, yes. But if you have an internal combustion engine, don't feel shy. So if I buy one, I will emit as much CO2 as if I'm driving this car for 100,000 kilometers. So transition doesn't have to be made tomorrow, but of course, we will have to end little by little. Here you have like an emissions distribution. This is from Visual Capitalist, which is a website that shows this kind of very graphical values, showing electric vehicle on the left, combustion on the right, and hybrid in the middle. So basically, how much is the energy used in fabricating an electric car, which is much higher than a combustion car, then the emissions while they are during the production of it, and then during the operation of them. So values are similar. We are going to be more clean, more efficient, because we are going to minimize the emissions with electric cars, but replacing a combustion car today that is new or is 3, 4, 5 years old doesn't make sense, because at the end of the day you will emit more. You will make a peak of emissions. And also the technology is evolving. Right now, basically, most of the market share is combustion energies, hybrid energies, but then they are dealing with battery electric vehicles or also fuel cells. So these are growing, and you cannot really extrapolate what will be the technology that we settle. Everybody who is working on that, they know that there is several technologies on the way. But the important thing is that there is like 1.2 billion combustion cars in the world, and 1 million, it is 1,000 times less electric cars than combustion cars. And you cannot replace that in one day, not without a huge emission of CO2. Only in Europe there are 250 million cars. So that is an important change that has to be tackled. And then if you look at the emissions, and because of the very restrictive emissions, the combustion cars are minimizing the emissions to the point that when you look at the complete balance of buying and using, don't worry to sell your car right away. You will have to buy, and the next car will probably be electric, but don't rush. Use it until the end of its life, and you will make a favor to the environment. And that is something important. And among the emissions, it is not only CO2, we are having plastics, micro nanoplastics everywhere in the environment. And this is also like another general view, and in this case I will end up touching health and other considerations, but I think this is also interesting. There was a time that finding a bottle in the ocean was a weird thing, and typically it was a message to the person who was lost in an island, help me, lost here. So it was like this. Nowadays the ocean looks a bit different, something like that, and the one asking for help is actually the fishes in the ocean. And that is a big problem, because actually per year we are just tossing around like more than 400 million metric tons of plastics to the environment. So that's a huge amount. And you get these things that you see, but these break up and then they go down into micro that you can still see it, or nano that you don't see, but you will breathe and you will eat directly or indirectly. So that's something that ultimately goes back to not only to the environment, but eventually goes back to you. And that may have an effect. Actually, when you're looking at the figures, and you see the emission of CO2, the emission of plastics, they are growing a lot and quite in parallel, because in the end all of them reflect human activity. And the other thing that also, but that's more academic, is the number of papers talking about contamination by micro nanoplastic. If you look at Scopus or any database, you will also see that there is a ever increasing number of papers working on that. Why? Because there is a concern, because we want to know. And what are these papers talking about? Anything. They are talking about from physiological effects on the bodies, to environmental impact, to how to process, to how to degrade. It goes to any part. And actually that was interesting, because we have been working with people working with the food science about how these plastics is affecting our body in the digestive systems. You know that in the end, your health, your body depends a lot on the biota, on the microbiota of the intestines. How that evolves is affecting your health indirectly, something that time ago people didn't know. In India you know better, because you know yogurt and you know many things, which is very important for us, but in other places we were not that with such a good knowledge of how important it is, and now we are getting aware of that. But now the people is interested, for instance, PET, polyethylene terephthalate, this kind of plastic, is one of the largest produced polymer, and the fourth layer, not only one of the largest, but the number 4 in production. So there's a lot of PET, which is lost to the environment. So the kind of things that we did with these people in food science is that they have a gastrointestinal simulator using actually real feces mixed with the plastics, and observe what happens in the oral phase and in the gastric phase and in the intestine, and how the plastics evolve in the digestive system. We were looking at several plastics, one of them the most important, PET, polyethylene terephthalate, to see how this was affecting us. And so you were looking at the microbiota during the colonic fermentation for healthy people, and in cases where you don't add any plastic, and when you are adding plastic. And what you observe is that there are significant changes at the phylum. We had a biology person here. You were from biology? No, you. No, there was a person doing something about biology. Okay, whatever. I'm not an expert either, but there was changes on the microbiota population at the level of phylum. And in the person where you are giving plastics, you see like a dramatic decrease within 70 hours in the population of these bacteria within your microbiota. And that has an impact in your health. And actually, the other thing that we are more interested in is what happens to the plastic in the digestive system. The PET is affected. You have a little effect when you are in the mouth or in the stomach, but when it goes into the colonic fermentation, you start to see that the plastic starts to look more dirty, more degraded, more things are changing on it. And then what we do, and this is the first time I am talking about the technique I use, which is Raman spectroscopy. Do you know why Raman spectroscopy is called Raman? Exactly. Because of Professor Raman, Chandrasekhar Venkata Raman, who discovered inelastic the dispersion of light, which gives you information. And the nice thing of Raman spectroscopy is that uses visible light, and then you can connect to a microscope and to make maps. And tomorrow I will be talking, or after tomorrow, I don't know exactly, about the Raman spectroscopy. But here, basically, with a microscope, you can look at the plastic and select this kind of grid and make a spectra in many points, for instance, 60 points, to characterize this plastic. And Raman, you will see, it gives you a lot of molecular information about how the material is. And in this case, that's very important, because when you are characterizing a plastic at the beginning as the pellets that you are giving to the digestive system, you make 60 spectra and 60 positions, and here you have the 60 spectra. It looks like one. Everything is identical. It's a very homogeneous product, which is basically the polyethylene terephthalate. And after it goes into the stomach, into the small intestine, and into the colonic fermentation, you will see how at different positions you start to see some changes. You see that already in the gastric, you see some changes between the 60 spectra. Some of them look different. Also here, you have some changes in the relative intensity of those ones. So this is telling you that the plastic is changing in a not very homogeneous way, but you can see that here, there is no longer the same. There is a progressive degradation of the plastic already in the stomach. And then when it goes to the colonic fermentation, you even see much more changes, and even some of them, like the relative intensity of this band here that was very constant on the fresh system. Here you can see that the relative intensity changes a lot, and even that peak almost disappears in many positions. This is telling you a very major degradation of the PET within the colonic fermentation. Also here, you also see that there is a lot of the crystallinity of this polymer. Polymers tend to be semi-crystalline with regular structure, like in this drawing there, like a plane, it's something like that, very regular. All these things. So the body is affecting the plastic. And that is also like an informative information, to the point that then you can use nature and enzymes to degrade. We have a collaboration with a colleague developing enzymes to degrade PET. And I shared with you, because it's a very nice drawing, how they put the enzymes designed to attack. So people working at biocatalysis is now doing engineering on enzymes, using wild enzymes to modify them, to make selective, to attack and degrade plastics. And that is something that is happening. And with Raman, you can monitor the degradation of this polyethylene terephthalate into different kind of components very quickly. Of course, now a lot faster than what is happening in the digestive system, because this is already very dedicated and very focused analysis. So, and you can get a lot of products out of the polyethylene, and then you start to get the monomers and dimers from the polyethylene terephthalate, and then you can use that for further fabrication. So that is something which is telling you that nature is already able of coping with plastics. Our system is already coping with plastics to some extent. You can engineer enzymes to cope and to degrade the plastics. But of course, managing and degrading the microplastics depends on many things, because not all the plastics have the same reactivity. For instance, the ones that we were looking at in the digestive system is polyethylene terephthalate and polylactic acid, but these have carbon-oxygen carbon bonds that they are more reactive and that they are more easy to attack. The same thing happens with nylon. You got amide bonds with carbon, nitrogen, hydrogen. So these things are more reactive and they can be more easily attacked. And other times, what you also do is, because when you start to decompose a polymer, you start to get many monomers, and then you can do something. Something that you can do is to put a co-reactant, because when you break something into many components, then the reaction may happen, and that can be a cause. But catalysis is not only converting, it's converting to something. And to steer selectivity, you need a catalyst, or sometimes you need a co-reactant. You put something that the fragments like, and then they go in that direction. So this is kind of approaches which are being used, like co-reactant to steer the selectivity. Other people have discovered, for instance, for producing hydrogen from water, if you are adding small amounts of plastics into the water as a sacrifice component that degrades, you trigger the emission of hydrogen with electrocatalytic treatments. Or you can use these polymers just to transform them into chemicals and hydrogen. Actually, there are some processes basically to do a pyrolysis into carbon fibers and hydrogen. How we apply that? Well, remember that slide. Some plastics are more easy to convert than others. Some are more reactive, some are less reactive, so that changes. So some of the upcycling strategies will be more challenging when you only have carbon-carbon bonds, like a polyethylene, polypropylene, these kind of materials. And that can be very energy demanding. So in that case, you need efficient activation. There is an increasing number of people who is starting to use, for instance, microwave activation. So they will have a system here where the fluid, the oil is passing through, and this little bluish thing that you see here is like a porous silicon carbide. It's basically like some kind of porous cylinder made of silicon carbide. Why silicon carbide? Because it absorbs very efficiently microwave radiation. And so when the plastic goes through it, the degradation is much more intense, and then you can convert it more efficiently into something. And into what? Well, people is working on making carbon nanofibers and hydrogen. So these are the two kind of the products that you can obtain from polyolefins in general. And this is kind of development that is taking advantage of a much more efficient use of the energy through the microwave heating in the system. And in our case, we have a microwave reactor like this one, which is a monomode reactor. It's like a 70 centimeter long. So we can do many things there, and that is very convenient. We were using it for other applications, and now we are going to work on these kind of applications because we see a great potential, and we have systems that allow us to go in that direction. What is the nice thing of microwave? How many of you are acquainted with a microwave? How many of you that have a microwave at home? At least, only you. You don't have microwaves. You don't like heating with microwaves. Okay, it's very efficient. Now, microwave in the kitchen is a multi-mode. A multi-mode is not an optimized system, it's not very energy efficient, but you can see that they heat very quickly, very fast. When you go to monomode, what you have is a standing wave, which is inside the cavity, and basically the catalyst is at the maximum intensity of the standing wave. So the heating is with the maximum possible efficiency that you can get with microwaves. And that is important because the field has like a local maxima. So when you are making a synthesis, and if you are flowing, basically, what happens is that you have like hot spot, cold spot, hot spot, and this is like 70 centimeter. But because this is a flow system, we have liquid flowing through it, then after a while, everything gets homogeneous, so you get a very homogeneous heating within it, and then you can control very nicely what is happening within the system. And the energy efficiency is much better. And that is important because another challenge to do things is to minimize the energy to do something, some kind of a leveraging effect, so that to do something, you minimize the energy that you need to do that. How can you intensify a process? Well, in a rough approach, you may consider like these 5 key pillars. One of them will be the integration of reaction and separation. Separation is important because many reactions are equilibrium limited. So once that you get a significant progress in the reaction, well, that's it, because the reaction is equilibrium limited. If you remove some of the product selectively, then the reaction won't be equilibrium limited. And that can be made in many manners, distillation, reactive distillation, whatever. But another approach, which is also interesting, is microstructure reactors. Microreactors can be very good for temperature control, heat control, many things. And for instance, we have an experience where we were combining both microreactors and separation to increase the reactivity, which I will show you in a moment. Another option is multifunctional catalysis. A catalyst can be acidic, can be basic, can be redox, or can be combinations thereof. And basically, that's important because when you get one side here and another side here, like a acidic and redox nearby and the molecules sit nearby, you are getting products that you don't get if they were separate. So that is also very important. The dynamic operation and modulation, that's very important. Sometimes you have to modulate the conditions of the reaction. And in this case, and we are working a lot lately in starting microwave things, when you want to modulation, the control of temperature with microwaves can be extremely fast, which make it very, very dynamic, and that can be very important sometimes. And then the nanoscale engineering, you can not only engineer at the large scale, but also smaller things. So the two intensification instances is separation in a microreactor, pervaporation. You know what is pervaporation? which is basically permeation evaporation, like you are making a reaction through a membrane reactor. But this is a membrane that doesn't allow everything to go out. It's a membrane with a pore size that one molecule will go out and the other one will not. And in such a case, the one that goes out, if at the other side you have vacuum or something, it evaporates, and so it's pervaporation. That's very good because in reactions which are equilibrium limited, that can be very interesting. So we were doing that with glycerol. Glycerol is a very interesting molecule, which is also a byproduct from renewables. And what can you do with glycerol? Many things, too many things. Because glycerol is very nice for a chemist because it's very reactive. But because it is very reactive, as nice as it is for a chemist, it is a headache for a catalyst person because I want you to go there. No, it goes everywhere. No, that's no. No, I want selectivity, focus, go to that product. No way. Glycerol has a very big reactivity. You want to make oxidation, you want all kinds of things. That's a headache. You cannot control. So in the end, it's like I said before, you need a partner, someone a co-reactant to steer selectivity. Okay, you like many things, but here you have a Ferrari. Goes to the Ferrari. You need something. How do you do that? Well, there are many processes where they do that, like adding different kind of co-reactants to steer the selectivity. Like, for instance, this kind of reaction. So one of the processes that I like is the one to make glycerol carbonate. Basically, it's the reaction of glycerol with CO2. And then you will make a carbonate, which is basically this ring that you observe here. So you have the 3 carbons of glycerol, and then the carbonate binds to these 2 hydroxyls, making this. And this is a product that basically can be made in different manners. Biologically, with enzymes, and then you will get products and the glycerol carbonate. Or with supercritical CO2, and you get glycerol carbonate. Or you can use something that behaves like CO2, urea, which is also a byproduct. And if you use urea, the reactivity of urea is equivalent to the reactivity of CO2. Because in the end, the urea, basically you get that CO group and 2 NH2 groups. The way it binds, for instance, to diols is the same thing that the carbon dioxide will bind to diol. It will make a carbonate. And 2 ammonia molecules will be coming out. So you get glycerol carbonate and 2 ammonias. So we have a catalyst, which is cobalt oxide on zinc, which is nice, it works nice. Here you have some Raman spectra. Basically, it's a catalyst with cobalt oxide and zinc oxide. So the Raman spectra show you Raman bands of cobalt and Raman bands of zinc oxide. And interestingly, we are mixing it. It's just made by nanomechanically mixing these 2 powders. If you increase the temperature, you get some additional phase of the reaction between cobalt and zinc, which is the spinel, this phase over here. But otherwise, you will have the cobalt, which is distorted by interaction with the zinc, but still cobalt. Now, the nice thing is that this cobalt, which is affected by zinc, but remains like cobalt, is the active phase. And when you get the spinel, the system is not working. So it's an incipient interaction between the cobalt and the zinc. And what you can do is to monitor the reaction using Raman or infrared spectra. These are, for instance, the infrared spectra of the glycerol and urea together, the glycerol carbonate, everything. So you can monitor the reaction, how some reactants are being consumed, how some products are being formed, and you can use it to quantify the reaction. This is the catalyst that we treated at 500, where you get the mixed zinc oxide, and it's not working very well because we want to make glycerol carbonate and it stays here. When we use the catalyst without high temperature, just by mixing the 2 powders, the system is much more efficient and it makes the carbonate. There is another product which is in between, the urethane. The urethane is when you make the carbonate, only one is connected. So this is half a cycle. So that intermediate becomes the dominant in the temperature that was treated at high temperature. But in this case, that one is basically an intermediate and then ultimately goes to the final, much more efficiently than in the other one. Now, these kind of reactions basically is you get the glycerol and the urethane, you get this urethane when it reacts with urea and releases 1 ammonia molecule. And then when it closes, it will release the another ammonia molecule. So you have 2 ammonia molecules that are there, but this is an equilibrium. So the reaction, if there is a lot of ammonia, say, okay, enough. But if you take the ammonia away, things will be okay. So you think that the reactor is like a barrel, and you have to take things out of this barrel. So then you are shifting the equilibrium. So the reaction from glycerol to the glycerol carbonate will run without equilibrium limitation. Can we do that by removing ammonia? Yes, and that was a cooperation we did with a group in the Hong Kong University of Science and Technology with these microreactors. This microreactor is the size of a stamp. It's like very small. It's micro reactor. It can be. You can put in your pocket. You can put many in your pocket because they are tiny things. And it's just stainless steel with a very big porosity, 0.2 microns. 0.2 microns is very big porosity. The glycerol carbonate, the ammonia, everything will go through it. So this is too big porosity, but this is just a preparation of a porous substrate to make something special. And so what we did is that we have a lot of grooves, these kind of little grooves over the reactor. You see it's just 1 inch by 1 inch on one side, and on the back side basically is this porous material. From the side it looks like this. You have a lot of channels. And why we do that? Remember that this is a high porous metal, stainless steel. And then what we do is to put on top of it the liquid feed so that they will go through these channels and they will react. And what do we put in these channels? Well, a catalyst. And so the channel is like that. Remember, this is always a porous stainless steel. So what we do is to put a zeolite, that we grow a zeolite on the surface of it at the bottom. And then inside the channels, what we do is to put a catalyst, this cobalt zinc catalyst that was very good to convert glycerol into glycerol carbonate. And then we put the two things together. You can put a zeolite at the bottom and the catalyst in the channel. So in the end, okay, this is characterization. Inside, you will see that we have the catalyst inside the channel, and then we have a pervaporation unit. Basically, the microwave, the microreactor is here. Here is a vacuum line connecting to the bottom of the plate where we have this zeolite grown, and from the perpendicular to the screen, you will get the reactants in and out. So we have 4 scenarios. The microreactor per se, which is nothing special, is just porous stainless steel. You can have the porous stainless steel with the zeolite grown at the bottom. And the zeolite grown at the bottom is very interesting because the porosity is no longer the porosity of the stainless steel, it's the porosity of the zeolite. And now you are dealing with a molecular sieving system. The porosity of the CSM5 allows ammonia to go through, but glycerol and glycerol carbonate cannot go through. So you have an instrument to selectively remove one of the reactants. The other option is to say, okay, I put the catalyst on the porous stainless steel, but no filter down here. Okay. And then you can get the complete package. You can put the catalyst in the channels and the zeolite at the bottom. In that case, should be ideal because you have the catalyst that is doing the job and the filter, the zeolite, that will help you filter out the ammonia and go beyond the equilibrium. And so here is the performance. Of course, this is just nothing special. This is the microreactor. You flow, well, you do get some conversion. This is what happens after 20 seconds at 145 degrees centigrade. Now, if you put the membrane, there is a natural reaction and you're removing some ammonia, so the conversion increases a little bit, not much. If you put the reactor but not the membrane, okay, the reaction is running as usual, nothing special. But if you put the catalyst and you put the filter, then the reaction is much more efficient because the reaction is happening and will never get tired because it will never see that there is ammonia left because ammonia is filtered out through the CSM5. So these kind of ideas for process intensification is very important. And there is also another value. If you look at the process, when the reaction feed goes into the reactor channel, there are bubbles. When you are doing pervaporation, bubbles because ammonia is being produced and we are at 140 degrees. When you are doing the vacuum for the pervaporation, there are no bubbles because ammonia is just taken away as soon as it is formed. So it makes the system even more efficient because when there is a bubble, there is no reactants. So everything becomes better in these kind of systems. And that's why you go into better and better. And the other kind of process intensification application will be, for instance, the use of radiations. Some of you is working with photoelectrocatalysis. In this case, this is about microwave. Okay, fine. Microwaves. The typical monomode, well, no, that's not the, well, yes, okay, forget it. The monomode and multimode. The multimode is more typical because it is in every kitchen, in every place, and basically it's not that efficient. Basically, the microwave is resonating within the cavity, and at the end of the day, well, at the end of the minute, your coffee will be hot. Now, if you do the same thing here, the heating efficiency is much higher. Now, why don't we all use monomode microwaves? Because the monomode microwave, you get a standing wave, which means that the wave at a given position has a maximum. But the shape, the intensity of this wave is what it is. And it depends on how the cavity is designed and how the waveguide is designed. So you may have a very good monomode heating system for a given shape of a glass or a bottle or whatever. But if you use another shape, it won't be very efficient. The multimode that you have in the kitchen is good no matter what you put inside. So it is less efficient, but at least you have a random distribution of the radiation inside, and it will be heating things more efficiently. So people is using both for research and only the multimode for the kitchen. Basically, the classical one that you have in the kitchen or regular things is like that. So it's just bouncing all over. And in the other way, you have the standing wave, and over here, in the middle where you get the maximum intensity is where you put your reactor. Advantages of the classical one, you can buy it in the corner near you, and it's simple, but the energy efficiency is lower, and you don't really have a good process control. If you want to use it for catalysis, we all tried, and you get nice results, but the next day you want to repeat, and it's not reproducible, because this is just for heating a coffee, not to do catalysis research. So they have industrial ones intended for research on these kind of systems. Now, on the other hand, when you go to the monomode, they are far more complex. Okay, so basically you design a monomode system for a given kind of geometry, for a given kind of material, for a given kind of application. It's more like a tailor-made suit. Okay, but in return, you get faster heating. And what do I mean for faster heating? How fast is fast heating for you? How many degrees per second is fast? 10, 100, 1,000, a million degrees per second? 10 degrees, okay. With a monomode, you can heat up to 500 degrees per second. So you do like this and, my God. So that's very, very fast. And I went to the other screen, okay. So that can be very, very fast heating. And that means you can have a run out, can lose out of control, but at the same time, if everything is well managed, you can have a very accurate control. In some reactions, accurate temperature control is important. Sometimes you have a catalyst that is being deactivating, and then you need a regeneration, and then go back. And this regeneration can be like a temperature peak. You can do those things very efficiently. And so you have a lot of control in these kind of systems. And it also has the capacity to very efficiently heat materials that typically you don't get easily heated with the normal microwaves. And because this is very fast, it will also give you a much better process control. And of course, energetically, it will be much more favorable. Okay, this is just a photograph of a microwave heating monomode. So this is like the waveguide, which is basically a tube. It's a square tube where the microwave wave is moving. And over here is the cavity. And this little thing that you see gas in, gas out is basically where you have the reactor inside, a reactor like this, where you have the zeolites or whatever to run the reaction. This is the temperature profile in a normal heating where the heat is coming from outside, and this is on a microwave heating. So in the case of a conventional heating, basically, you will be heating from outside in until everything is more or less heated. And that can be not very efficient. A lot of energy is lost in the diffusion. On the other hand, in the case of microwave, because the microwave penetrates the material, it's heating all the material, and it's providing a more efficient heating mainly from inside out. Sometimes you actually, it's the reverse. For conventional heating, because you are heating, this is the the outside is the warmest because it's where you're heating, and then the heat inside takes a while. In microwave, because the radiation is absorbed, sometimes the outside is dissipating, and the outside is a bit colder than the medium or the inside. So temperature profiles are different, and sometimes you can see that maybe on the sides is colder than the inside, but that's part of it. Now, which kind of materials can you use for microwave? It depends. Would you put a spoon with your coffee inside the microwave? No. No, because the spoon is a metallic spoon, I mean, not a bamboo. But a metallic spoon will be like an antenna, it will create sparks, it will create problems. So you cannot use these kind of things. And so when you design a reactor, you have like 3 categories of materials. Some of them is transparent material. Transparent material doesn't interact with microwave, which is good because the microwave go through them. And that is a material that has a very high penetration depth. So it allows you, the microwave, to go through it without a significant decay of the power. And it will not heat. So the energy which is absorbed by that material is very little. Material like that, Teflon and quartz. Well, that's good because if you make a reactor, the reactor can be made of Teflon, can be made of quartz, and you put the catalyst here, and then the gas or the flow go through it. And a Teflon tubing or a quartz tubing is convenient. Glass tubing is convenient. Then you have another kind of material, absorbent material, the one you want to get hot. That will be inside, it will be the catalyst. It's a material that will absorb energy, and of course the penetration will be lower because it is absorbing the microwave radiation, so microwave will not penetrate too much because it is being already taken and absorbed by the material, but the material is getting hot. So basically this is the absorbing material, and this is the key element. And then you have another kind of material, which is the opaque one. The opaque one is a material that does not allow the microwave to go through, and that doesn't get heated by the microwave. So it's good for nothing? No, that's the containment. All the microwaves, they are metallic shielded because the metal doesn't heat and doesn't allow the microwave to propagate. So that is very interesting. For that reason, we are using this transparent material as the reactor body, this absorbing material as the catalyst body, and the opaque part basically as the containment. Okay. So this is kind of the design that you will see on these materials. And okay, well, that is similar to what I already said. And the way it looks like is like this. The cavity in the end is something like that. The reactor that we use is made of Teflon or is made of quartz. And how do you measure temperature? You cannot put a thermocouple because a thermocouple is metallic. So it will be an antenna taking the microwave out. And then the microwave goes to you, which shouldn't. So basically you are using fiber optics, or you are using infrared cameras, you know, like these ones, but instead of taking a photo of a dog or whatever that is, basically it will give you the temperature profile in the reactor. And now there is a new fiber optic technology which is coming to the market and that we are going to try, which is very interesting because it has a Bragg grating. So it's a fiber optic with a Bragg grating. So because of the temperature, this little grating changes, and then you get diffraction pattern of the light with it, and then it can tell you the temperature inside. It's a very interesting, very elegant system, and we are going to play with it, but that can be good because this can provide a very good measurement. You know that this PowerPoint is alive, it's changing slides on its own. I don't know why, okay. But anyhow, the other challenge is when you want to go to industrial catalysis, you are not dealing with a powder, you are dealing with a shaped catalyst. A shaped catalyst can have the shape, for instance, of a brick, a monolith, or can be a ring or whatever. So different kind of pellets or different kind of structures. And with this infrared camera, you can get the temperature profile within these particles or within this catalyst to better monitor what is the temperature profile and how they are behaving, or even if there are like hot spots in the system of these materials. So this is a part of the challenge. And the most interesting thing when you are dealing with microwave is that if you compare a given reaction made by conventional heating or made by microwave heating, and sometimes you find something interesting. The apparent activation energy changes. It's not only that a reaction happens at much lower temperature, which is one of the advantages of microwave, it's also that the apparent activation energy changes. So we are changing the reaction mechanism. This is quite recent because in photocatalysis, people already know you are changing the orbitals because of the interaction with light. You are changing the rules, but with microwaves, it would appear that there is something else, not only a very efficient heating effect, but something else. And these changes in apparent activation energy is actually telling you that there is something else. So that's part of it. And now this is another moment that I want to tell you another way of another application, which is synthesis of nanotubes. And then maybe that can be the end for today, and then we can continue tomorrow. Sakar, that good?
Yes, sure.
Okay. So another application for microwaves is because of this long flow reactor, you can also work of making materials more efficiently than before. And titanium nanotube is a very interesting material for multiple applications. So here you have some applications in photocatalysis, of course, biomedicine, solar cells, supercapacitors. The way they typically make it, for instance, with a templating or anodic oxidation, where you develop on a surface the titanium nanotubes that they grow. Another process is the hydrothermal synthesis. In the hydrothermal synthesis, you make, for some reason, my presentation is going faster than me. It's changing on its own. I must have some kind of automated thing I did by accident. Okay. I have just to tell it to stop. Okay. The way you make titanium nanotubes is that usually you put titanium and sodium hydroxide, and you take it into a microwave or into an autoclave or into whatever. Basically, you heat until the sodium hydroxide reacts with the titanium into nanoplatelets, nanosheets, which is sodium titanate. So these are like platelets, like flat things of sodium titanate. And these sodium titanates are flat, they're like this, and then when you wash them after the synthesis, what happens is that the sodium titanate, you can wash away the sodium and then it will scroll and it will make a roll. Sodium is away, what you have is titanium nanotube, well actually nanoscroll, because it's not like a tube, it's like a rolling up something, but formally it's like that. So this is just moving along. Now, you can do the same thing with microwaves. They do that in a batch reactor, but we say, okay, why don't we do that in a flow reactor? Because then you can have additional control systems. The first one is that when you make it by batch, people is working on that to make titanium nanotubes, Syria nanoshapes like nanocubes, nanorods, nano-octahedra. You can control that, but the productivity is very little. So if you make it in continuous flow system, you can continuously be producing something. That's why we decided to use this microwave flow system to do that. And basically, this is the standing wave, and then we flow into it this solution of sodium hydroxide and titanium. And what you get at the end of the process up there is the sodium titanate. Now, the way this sodium titanate is made is controlled by the temperature and by the pressure and by the flow. So you can control much better than in a hydrothermal synthesis, which is in a closed system, because you have a continuous feed and a continuous output. And so here you can play 1, 2, 3, 4 bars. This is a water solution, but we have a pressure valve in the system. So you can go at high pressure, controlling the pressure, which is good because then you can go at more than 100 degrees without boiling, because if things boil, the efficiency of microwave is killed. But if you are dealing with 2, 3, 4 bars, it will not boil at 1 or 110, 120 degrees C. That allows you a much more efficient process. So you can play with the pressure, you can play with the residence time, you can play with the temperature, and then you can end up making titanium nanotubes and getting quite a narrow control in the diameter of this. These are the nanosheets of the sodium titanate, but then when you wash it and they scroll, they make tubes, and then you make titanium nanotubes, and they will look like this. And what you can get is a very accurate control, like you can see here, about 9 or 10 in the internal diameter, in the outer diameter, the internal diameter, so the opening, the lumen inside is about 5 nanometers, and the length is also rather constant, around 180 nanometer long. Of course, Raman spectroscopy is always there. We can look at the different materials that we are having on the precursor and on the product. So here you have basically the titanium nanotube Raman bands. And the nice thing of this system is that because you are going from this material into the tube, And okay, these are different controls, but the key message is not about this, but the possibilities, because when you have the sodium titanate and you wash away the sodium, it will scroll into the tube. Now you want to make photocatalysis, and titanium N02 is a nice guy, but it is even a nicer guy if you put an active phase on it, which out here. So the sheet will scroll into this tube, which is not exactly a tube, but behaves like a tube because it scrolls. So the idea is that we can put, when we are washing, an active element that will enter into it. And we can control whether it goes inside the tube, at the interlayer, or outside. And we were doing it with silver, so that you can get the silver nanoparticles getting inside the main tube, at the interlayer, or even at the surface. Here, for instance, you have a bright field. So it is preferentially larger ones collocated in the tube and smaller ones in the interlayer. And the nice thing of that is that because you get the silver nanoparticles, and these nanoparticles in the tube get a longer shape, they absorb more closer to the visible, and then this photocatalyst can be working not only with UV light, but also with visible light. And you can use it for photocatalysis to degrade whatever. That was diclofenac, which is an endocrine disruptor. But there is another value. When you are putting this silver in the lumen or interlayer, this silver particle will not leach out, will be stable, will have the photonic effect for the photocatalysis. And when you make toxicity of this catalyst, toxicity against the skin or any reaction, the toxicity is much lower because the silver nanoparticles are not exposed. They're doing the job, the light goes there, the photonic enhancement is happening, the photocatalysis is happening, but if this is released to the environment and eventually goes to you, the toxicity will be much lower because this silver is not exposed. So there is even the values now that they are talking about safe and sustainable by design and these kind of things that politicians like to put in regulations, and then say, okay, you find out, you are the scientist. In the end, you can get and do that kind of things. So the catalyst is at the core of everything, which is a good end for today. And tomorrow we will continue with more things. But of course, that was what Sagar said this morning, that the catalyst doesn't change. But then, of course, he was adding an explanation that indeed it does change. So the definition of catalysis is not exactly this ideal thing that the catalyst is not changing, but something else. The catalyst is doing the job, but the catalyst is aging, is transforming, and that is a key part. And that will be the core of the activities that we are going to do. How the catalyst looks like, how does it behave, and the most interesting, how we connect the structure with the activity, so that we know this kind of structure is doing this behavior, that kind of structure is doing that other behavior, and that will help us to get into this molecular understanding of the structure-performance relationships in catalysis. And I guess that ending with the person who was beginning this morning is a good way of ending today.